Alright, so now we are going to look at net force. Now I'm going to be moving pretty fast through this presentation, so you will want to be pausing often so that you can take full notes on this. This is a very important concept, and when people mess up Newton's laws of motion, usually it's this concept of net force that they mess up on. Alright, so Newton's second law, F equals ma, we're going to make this one little addition of putting a sigma in front of F. That sigma means sum. It's a mathematical term meaning the sum of all the forces. So when we look at how an object might or might not change its acceleration, to really fully understand this, we have to look at not just one force, not just the applied force or push or pull, but all the forces acting on it. This is why when you push something across the floor, when you stop pushing, it stops, because you have an unseen force, a force of friction that's acting on it. And if you want it to stay in motion, you have to keep pushing it. You have to overcome that force of friction in order for the object to stay in motion. All right, so let's look at a 3 kilogram box on a frictionless surface. If you apply a 6 Newton force to the right, then it's going to stay going to the right. All right, the net force acting on it is equal to 6 newtons. Divide that by 3 kilograms and you would have an acceleration of 2 meters per second every second. So the box would continue to accelerate at 2 meters per second every second. So after 1 second it'd be at 2 meters per second, after 2 seconds 4 meters per second, so on and so forth. But of course this is a fantasy example. There's no such thing as a frictionless surface. All surfaces have friction of some kind. So let's just say we are pushing a 3 kilogram box with 6 newtons of force, but there's 3 newtons of friction. Well, we have to take this into account when looking at the acceleration. So sigma F is the combination of two forces, the applied force plus the force of friction. Because they are in opposite directions, we have to call this force of friction a negative force. So when we do 6 plus negative 3, we get 3 newtons. Then we can apply that to our acceleration equation. Acceleration is equal to net force divided by m. 3 divided by 3 gives us 1 meter per second every second. So obviously in this case we're going to have a smaller acceleration. Now of course you cannot push something and have it accelerate forever and ever. At some point the force that you're applying and the force of friction will be equal to each other. So we'd analyze that this way. Exact same way we analyzed it before. We have to add together the net forces acting, the force applied plus the force of friction. So that's a force applied, that's the force of friction. They're in opposite directions, so one of them has to be negative, and I'll just say that to the left is negative. So the net force acting on this object is 0 newtons. So if you're already pushing it across the floor and you're applying a force of 3 newtons and there's a force of friction of 3 newtons, then that means you're going to have an acceleration of 0. Now this does not mean that it has no motion, that it's not moving. It just means that it's not changing its velocity. So in this case it could have a constant velocity going across the floor. And unfortunately, without knowing other information, we wouldn't know what that velocity is. We just know that it's not changing its velocity. And now let's say you stop pushing. So now the only force acting on it is the force of friction. Well, the net force here is just the force of friction. That's negative 3 newtons. We apply that to our acceleration formula, and we get an acceleration of negative 1 meter per second every second. So it's going to be slowing down until it comes to a rest, at which point the net force on it would be 0. So this is the chart that will help you decide whether or not an object is speeding up, slowing down, stationary, straight line, and constant speed, so on and so forth. You can go one of two directions. You either start on the side where you know the motion. If you know that it's going at a constant speed in a straight line, then that must mean that all the forces are balanced. They're canceling each other out. Or if it's stationary, it's the same thing. The acceleration will have to be 0. However, if it's speeding up, slowing down, or changing direction, then you know that the forces must be unbalanced, and you have a non-zero acceleration. You can also go the other way. If you happen to know that the forces are unbalanced, then it must be doing one of these 3 things. Or if you can see that the forces are balanced, then it has to be either stationary or traveling at a constant speed in a straight line. So, here I have a situation. 2 forces acting. What's the net force? 11, of course. Sigma F is equal to 3 plus 8. Here the forces are unbalanced. The object must be accelerating. How about here? Net force, 5 plus negative 10, giving us a net force of negative 5. Forces are again unbalanced. The object must be accelerating. How about here? We have a plus 5 and a minus 5. These two forces are canceling each other out. The net force is 0. Therefore, the forces are balanced in this situation. Therefore, the object has a constant velocity. It's either 0 or some non-zero constant velocity, but the velocity is not changing. This object is said to be in equilibrium. If an object is pressed against the surface, then the surface presses back. This is Newton's third law. If I push against the wall pushes back on me. Therefore, the wall is exerting a normal force. Or here you have a box sitting on the floor. The force of gravity is pulling it down. We call that weight. The box applies a force onto the floor. The floor applies a force back onto the box. We call that a normal force. So here's a free body diagram that shows all the forces acting on just the box. We've got the force of gravity and the normal force. By the way, the normal force is always perpendicular to the surface. And we'll focus a little bit more on that later. So here I have a box sitting on a table. I want to determine the normal force. Well, I know the force of gravity is pulling it straight down. Force of gravity can be found with mg, and it's in the negative direction, so it's negative 7.8 newtons. Is the box accelerating? Clearly not. It's sitting on the table. It's stationary, so that must mean that there are balanced forces acting on it. So the table must be exerting an upward force. That's the normal force. And it has to be equal to but opposite the force of gravity. Notice I use capital F's to represent the force. And then I do a subscript. And the subscript tells me what kind of force it is. So here we have a normal force. Here we have the force of gravity. All right, so here's an object in equilibrium. Pause until you can figure out what the missing force is. And I'm just going to start going through these. Pause as you get to them. So if I have 45 newtons, then this is in equilibrium, then the missing force is negative 45 newtons. Okay, what's the missing force that causes this object to be in equilibrium? All right, minus 20, yes. How about here? It would have to be 10. How about here? What must be the missing force? Negative 20. Oh, now see, I have a mistake here. Really, this vector should be quite a bit longer. If this represents 5 and that represents 15, then and the length of the vector tells us information about its magnitude, about its size, and really this vector should be quite a bit longer. My mistake. All right, here's another one. Determine the missing force. All right, 15 newtons. Good. Not too bad, right? All right, here we have two forces, or forces acting, three forces, but they are acting in different directions. Just like in projectile motion, we can separate things into x and y components because the x does not affect the y. The vertical does not affect the horizontal. So we can analyze them separately. So in this case, if we analyze all the forces acting in the y direction, there are two of them. So I'd give it a subscript y. And we have 3 newtons up, 3 newtons down, giving us a net force of 0. Therefore, if I were to solve for the acceleration, I would clearly see that the box is not accelerating in the up-down direction. It's not changing its velocity in the up-down direction. However, in the x direction, all the forces acting in the x direction, there's just one, 5 newtons. And so I could figure out the acceleration if I happen to know the mass of the box. And it's acting only in the x direction. All right, now a real-life example. We have a car. It's traveling at a velocity, a constant velocity of 25 meters per second, 2,000 kilogram car, 10,000 newtons of drag force. So there's a force of gravity straight down. It's not accelerating in the up-down direction, so there must be a normal force that counterbalances the weight. And I know that there's drag. Given that this car is traveling at a constant velocity, there must be a force to counterbalance the drag. So that would be the force applied by the engine. So it would look something, the free body diagram for the car would look something like that. Not too bad. Now, what if I am no longer pressing on the gas pedal? What would the acceleration be? Well, I still have the force of gravity straight down, the normal force straight up. The drag is still acting on it, negative 10,000 newtons. Well, I can figure out the acceleration looking at the net force. Now, like I said before, I don't have to consider these two in the net force. I'm going to analyze the horizontal and vertical separately. And since I already know that these two are canceling each other out because the car's not accelerating up down, only side to side, I can ignore them altogether. So the acceleration is equal to the drag divided by the mass, which gives us an acceleration of 5 meters per second every second. So it's slowing down, and really, I should have a negative there. So really the velocity is, it's losing 5 meters per second every second. All right, well, I wish that the force be with you. Oh, but there's something missing here. You know what? Star Wars had it wrong. It really should say, the net force be with you. All right, that's it. Signing out, and we will see you on the flip side.